not give us problems of gelation. And so we decided that from some previous work that we had been doing on another avenue, that perhaps it would be worthwhile to look at electronic and steric effects that you can get by the utilization of bulky phosphates. So rather than looking at just the simple complex, we started to make bulky phosphine complexes where the L ligand here is things like cyclohexyl or isopropyl phosphine compounds. I'll just show you the output of the results from our computer-controlled reaction system. Here is a plot. These are all data points that are taken online. And we can see that indeed this catalyst seems to behave quite well. Again, in a reasonable time, we're able to approach near quantitative hydrogenation using these bulky phosphine. So we were extremely excited now because this had good potential of being a replacement for the much more costly rhodium material. And if we go through all of the kinetic analysis, again, we can develop a reaction mechanism, and we do have values for the various rate constants and equilibrium constants that are involved. And this has been patented and it's been published a few years ago. The important thing here again is that there is this dead-end path of compensation with the nitrile, and indeed we have made compounds of this type to show that these do exist. We've attained values of these equilibrium constants, but fortunately we do not hydrogenate the nitrile again. So the catalyst seems to provide us with no gel formation. It's excellent activity. But when we started to look at the processability of this polymer, we started to encounter some difficulties. And these were traced to the fact that there was a little bit of microgel formation. And we can see this through the viscosity rise after the hydrogenation is carried out. So this is a disadvantage, because in polymer processing, the viscosity is extremely important with respect to the fabrication of the products that we wish to make. So we said, well, what is this high viscosity due to? We couldn't observe anything by NMR, by infrared, regarding the nitrile, but it certainly was there. So we did some studies on small molecules, and we found in the case of small molecules, the most important factor was that there was a little bit of a dimerization reaction due to reductive coupling of the nitrile, producing secondary amines. And of course, this occurs much more in the case of small molecules than it would in the case of polymers. What appears to be happening then, and there is precedent for this chemistry in organic chemistry, people have observed this in other situations. There's a formation of an imine. This imine then is hydrogenated to form this amine, and this now reacts with imine in order to bring the two monomers together. Now, if you imagine that R is your polymer chain here, you can see that if you do this with another R group being the polymer chain, this leads to a cross-link. And you don't need many cross-links in the case of a 200,000 molecular weight polymer to greatly start to change the viscosity. So very few events and you can start this out. So we looked at this and we said, well, how do we overcome this problem? And I must say we looked at it for a couple of days before we realized that the answer was right on that page. And the answer is here is, if this is going to happen, how about we put in a small amount of an amine. Let's say we take a amine, an octylamine or a butylamine, and use that as a capture agent so that if this does start to take place on the polymer, then we will intercept that imine group with the added amine. And we saw that primary and secondary amines, as well as nitriles, caused a reduction in the rate, which is not surprising because they could also complex with the catalyst. Nitriles caused a reduction in hydrogen polymer viscosity, but we needed pretty high concentrations of them. The best candidate were primary amines and ammonia. They caused a significant reduction in hydrogen polymer viscosity, and we could get the concentrations down quite low. So I'll show you just a few representative results. Selected a few different amines here. If you look at the top entry in this table, this is a situation where we don't add any amine, and you see that the intrinsic viscosity of the polymer solution at completion of the reaction is 1.93. If we compared this to the viscosity of the solution from the rhodium catalysis, the rhodium catalysis typically has viscosities of around 1.5 to 1.53. And you can see that we can indeed achieve that by using amines such as octylamine, tertiary butylamine, and we didn't do a lot of work with ammonia, but I think this should just be the plus as well. We could probably do better with the ammonia, but it's much harder to handle the ammonia gas than it is to put in a little bit of liquid amine. And fortunately, we did some pilot plant trials, and this worked exceptionally well. And it was a patented process, and we're about ready to put this into the main plant. In fact, we did a main plant run. It worked very well in the main plant. And then the price of rhodium dropped. It came down to $400 an ounce. And there were going to have to be some plant modifications for this catalyst because there is some differences in some of the treatment. So it was decided they would retain the rhodium technology, and this would be the insurance card for the future. I must say, for a while they thought that I rigged the price of rhodium so I'd have research money to keep this research going. So what we have then is we have two generations of catalysts. We have a rhodium catalyst, the Wilkinson catalyst or the tetrakis, and the bulky phosphine system. And for that matter, if you wanted to work in methyl ethyl ketone at low levels of polymer solution, you could use this catalyst as well. But when we were doing this work on the ruthenium and trying to get some ideas of the reaction mechanism in the intermediates, we found that it was really quite difficult. A lot of the reactions were very fast. And I must say I was sort of mesmerized at the time by some of the old reading I had done in the literature that if you go another period down in the periodic table, for instance, if you go from rhodium to iridium, or you go from ruthenium to osmium, you'll probably slow things down. So we can do some better model studies now, isolate the intermediates, and give us some clues. So I said, let's look at this osmium system, and let's try to see how it performs and if we can get information. And before I show you the result of the osmium system, I'm just going to show for comparison the ruthenium system that we talked about a little earlier. This is a profile for the ruthenium system, and you notice it works quite well. Indeed, we've got about 50% of reaction in a time of around 500 seconds, and quantitative hydrogenation in less than 3,000 seconds. So I had a new PhD student, and he went and he did the osmium system, and he came back with this result. This is supposed to be slower. So he comes up with this result, and he says, the reaction was over before I even had a chance to go for a coffee. He says, I just started the reaction, and he says, within 10 minutes, it was finished. So I said, you go back and repeat it again. And he did this many times, and actually you'll see a sort of a deviation from the curve here. We use a charging cylinder, and this thing was going so fast that the new gas that came in cooled the reaction down because we bring in this new slug of gas, and that's the reason for this sort of drop-off. And then when the reaction gets slower again, then we're fine. So this was very exciting, and we started saying, well, why? How come this thing is so active compared to the ruthenium system? And we did a full kinetic study here, and this appears to be the answer. This is the dependence on hydrogen pressure. And you'll notice I've drawn for reference here the two lower curves are the rhodium systems that have been being used. And you see in the rhodium systems that essentially there's a zero order behavior once you're beyond about 45 atmospheres pressure. In the case of the osmium system, which is the triangles here, there's a genuine second order dependence. And I must say that in all the time that I've been doing homogeneous catalysis and with small molecules, I've never seen something like this second order dependence. And indeed, in the literature for small molecules, this does not seem to be observed as well, because you're generally working at very low pressures where you're in the region of first order dependence. So it's a result of the fact that we're really upping the pressure. But you can see the tremendous advantage that we get if we use the plant operating condition of around 30 atmosphere, the tremendous enhancement that we get with this material. Of course, one says, do you have the same problems here that you might be getting in the case of the ruthenium complexes with respect to microgel formation? Well, fortunately not. You remember that sort of benchmark viscosity number of 1.52 before. In all of these cases where we essentially have quantitative hydrogenation, the intrinsic viscosity is 1.45. An extremely well-behaved system. It's hard for you to see, but we're working at about 12% polymer solids. So this is like honey, this material that we are hydrogenating. These are typical industrial operating conditions. We can accomplish the reaction in roughly 5 hours with quantitative hydrogenation and an acceptable viscosity. These are laboratory results. I must say that whenever we do things in the pilot plants, the results even get better because we have better agitation and we have better dispersion of the hydrogen in the solution. Now, why for the second order dependence? Well, we believe that this is a result of the capability of osmium undergoing multi-hydride formation. We have looked at the NMR and we have evidence for all of the species across the top. We have the equilibrium constant there. We have this equilibrium constant. We have evidence for the trihydride species. Obviously, from here we can do some kinetics. We have not been able to observe the pentahydra under the conditions that we can do our high pressure NMR. We cannot get up to pressures where we can get any measurable signal. So we have to infer that species, but that is the only way that we can account for the second order dependence of hydrogen. And the system does model very well. We have values that we have been able to pull back out, knowing the other constants for these other equilibrium constants in the process. So the situation where HNBR stands right now is when we started doing this work, there were test quantities, and the market has continued to grow. And we're at the extreme end here, where just a few months ago a new plant came on stream, and now HNBR is being produced by Bayer not just in the US but also in Leverkusen, Germany. We've been continuing to work with Bayer, and because of the osmium catalyst that I showed you, we've looked at the possibility of some new challenges. There's certainly a high demand for this material, and unfortunately in a batch process, you can only produce so much per time. So the challenges that we see ahead are the possibility of a continuous hydrogenation process, and I'll show you a little bit about why we think that would be much better. Possibly doing hydrogenation of the emulsion latex directly rather than bringing it out solution. And if I have time, I'll maybe make a comment on some work that we have initiated on on doing this reaction in supercritical fluids. Well, if we can do this on a continuous operation, obviously we'd have shorter turnaround because we'd be operating this 24 hours a day. Currently, on a batch process, the reactor is set up one day, the run takes place the next day, the reactor is then cooled down, the polymer is taken out, and the reactor is cleaned and set ready for the next run. So even in the current plant, you're only being able to do about 2 or 3 batches per week. On a continuous process, you're essentially bringing in your NBR, taking your HNBR out, and as long as your catalyst has a good lifetime and can do that conversion in the residence time in the tubular reactor, this should be feasible. It's obviously much more cost effective. It's not as expensive as a high pressure batch reactor with agitator. We can replace this just by a tube, packed, and with pumps. And there could be some advantages in easier finishing, and I'm not going to go into this. This is more on the downstream side of producing the final product. At Waterloo, we have set up a small continuous hydrogenation unit, and this is just a simplified schematic of it. The main hydrogenation reaction takes place in this tube. Catalyst solution, the polymer solution are brought in. There's obviously other things that are done here with respect to solvent addition, degassing, etc. Hydrogen supply, everything is fed in here co-current, and we bring out the material at the top, the separator to take out the HNBR, MCB, and the hydrogen is vented. Some of the results, the preliminary results that we have found is we've obviously now have to take into account a lot of the mass transfer aspects of this type of a reactor. As far as liquid holdup is concerned, the amount of liquid in the reactor is greatly affected by the hydrogen flow gas rate, so this is something of concern. Increasing reactor pressure reduces the effect of changes in the gas flow rate. The system does not appear to be severely mass transfer limited. The mixing is not excessive, so dispersion is not a significant concern. So it seems to be fairly well behaved on a small basis. This afternoon, Professor Pan, who is working with me at the University of Waterloo right now, she's a visiting professor from Xishan University, will present a paper on some of the aspects of the transport phenomena in this continuous reactor. I just want to show you the preliminary type of results that we have got. These are results for an NBR solution, operating conditions 403 Kelvin. This is a typical loading of catalyst like we have in a batch reactor. Pressures here either at 350 or 750 psi. Polymer loadings considerably less at the moment, and this is something that we have to look into more. But you can see that indeed, especially when we go to the 750 psi, either at 40 micromolar, or if we go to the 80 micromolar, that we're getting very close to quantitative hydrogenation in a residence time of around 1500 seconds. So we definitely believe that there is a good possibility here with some further work that we can design a process to use a catalyst to carry this out in a continuous mode. What I'd like to do now is just mention a little bit about some of the other challenges that we see. If we look at the overall picture at the moment of how do we make HNBR, or for that matter, how do we make any high-performance elastomer. First of all, there's a process to do an emulsion polymerization to make the base polymer. Then there is a post-treatment separation to bring the polymer out of solution. When we want to do the hydrogenation, then we confront a pre pre-treatment of dissolving that polymer, which we brought out of solution from the emulsion. The hydrogenation operation, say in a batch process or a continuous process, then a post-treatment of doing separation again. So there would be tremendous advantages if we could somehow take this emulsion and go directly to the hydrogenation. And that's something that we have been looking at, of trying to eliminate these post and pre-treatment entities, which are very, very costly. Now, of course, the big problem here is to try to find catalysts which can tolerate the emulsion. Because in the emulsion system, at least when you do a post-treatment, you get rid of a lot of the bad actors. You're only bringing out the solid polymer and some entrained impurities. But in this emulsion system, you have all kinds of things, leftovers from surfactants, many other things that are put into this particular recipe, which we know can cause problems for catalysts. And I wanted to show you some interesting preliminary results. And this is a bit of a busy slide, but on the left-hand side, I've listed, as far as rhodium and ruthenium are concerned, various catalysts that we have tried. And of course, the rhodium, the Wilkinson catalyst, and the tetrakiss hydride we saw before were very, very effective. Also, this bulky phosphate compound was very effective. Now, when you look in the emulsion system, you'll see that they don't work at all. No hydrogenation, very little hydrogenation. The big surprise, the catalyst that did not work in the solution phase is the best catalyst for the emulsion. It gives more than 95% hydrogenation. And it's something we still do not understand, why this seems to be so robust when you put it in to this messy emulsion system. So it appears that somehow there's something in the emulsion system that is changing the nature of this catalyst that performs much better and does not cause the cross-linking as before. Well, there's obviously something in the emulsion system that's causing problems for some of the other catalysts. So we have been looking, and unfortunately I cannot disclose to you the different types of things that are in this emulsion. It's information that is not available outside of Bayer, but I've been given knowledge of it, and so we have been looking at additives. And one of the things that we found is that for all of these catalysts, even the bulky phosphine ones that we had before, that we can increase the hydrogenation to about 95% by addition of ferrous ammonium sulfate. Reasonable reaction times, additive levels are reasonable, and this just gives some idea of the catalyst to the polymer loadings, which is typically what we would probably try to use. We have about a 20 mil of emulsion. We do use some MEK here to swell the polymer, open it up a bit, and this seems to have promise now of forming a direct hydrogenation on the emulsion. We even get better behavior if we look at an additive like carboxylic acids. Here, in the case if you don't have, this is going back to the bulky phosphine complex again. If you don't have the additive, no hydrogenation. If you put in an additive at these levels, this is additive per 0.01 grams of ruthenium. That's how much additive on that ratio we have there. And you can see here at quite low catalyst to polymer loadings, 99% hydrogenation and reaction times of about 4 hours. So there seems to be some good potential here of developing an emulsion process with a better understanding of how to take care of the impurities within the emulsion. The last thing I want to just spend a couple of minutes on is essentially the same type of reaction, emulsion, and then hydrogenation on the emulsion, but now using supercritical fluids. Try to get away from the utilization of the organic solvents and use a supercritical fluid to try to swell the polymer and to bring the hydrogen into the polymer to carry out this catalytic reaction. We have been doing some work initially in supercritical carbon dioxide, and some work we've been doing on looking at the catalyst properties in supercritical dioxide are quite exciting. It appears that many of these organometallics have pretty good solubility in supercritical CO2. The other nice thing about supercritical CO2 is that you can get complete miscibility with hydrogen. So you can get very, very high hydrogen concentrations, much, much higher than in any organic solvent. So this is another factor that is of importance. As I say, this is really in its infancy, and we're planning to move a lot more along this direction. But here are some reactions profiles run with our osmium complex that I showed you before. The polymer loading is about 7.5%, and 6,000 psi total pressure, where the pressure of hydrogen that we're using is typical of what we normally use in the other cases, around maybe up to 1,000 psi, the remainder being carbon dioxide. These are the 3 temperature levels. These plots are when we reach that temperature within the reactor. So that's why we have, in the cases of the higher temperatures, these conversions that look to be there at 0 time. Well, the problem is that we've actually started back here. This is time 0 when we're at that particular temperature. And you can see that indeed for the 150 degree, even though we don't have any solvent in the system now, that we're approaching quantitative hydrogenation of the polymer. Now, obviously, there's a lot of costs involved here of using something like supercritical CO2 because of the high pressures that you have, but there are also some tremendous advantages. At the end of this run, when you're finished, you vent off the CO2, your final polymer is there. You maybe have to, if you want to extract your catalyst, you might have to bring this out and wash this out. The catalyst levels that we're using, though, are so very, very small that actually even now, in some cases, catalyst recovery is not really regarded as a big concern. Well, I've tried to show you a bit of the kind of things we've done on HNVR production, because this is something that's kept us busy for quite a few years now and is continuing to keep us busy. But I'd like to just finish off by saying I think there's a great potential here for using homogeneous organometallic catalysts in polymer modification. And I've talked primarily about the top one here, how to stabilize polymers, in our case using hydrogenation. And we've seen also from some of the properties that I showed you, we can improve physical properties as well. But there are other reactions, of course, that are of very much interest with respect to polymers. For instance, we can produce reactive polymers for grafting or for further modifications. And there are a whole set of reactions, such as hydroformylation, epoxidation, hydroxymethylation, hydrocarboxylation, hydrosilation, hydroesterification. And we have now started to initiate programs in the ones that I put a green line underneath here, and the results look really quite encouraging. And there's quite a bit of interest in other labs around the world now also, where people in particular are looking at hydrosilation reactions and hydroformylation reactions on polymers. So I think this is a growth area. It's an area that brings together aspects of polymer science and organometallic chemistry, as well as a fair amount of chemical reaction engineering. I'd like to finish off by acknowledging a number of people that have worked with me over the years. The first work done on the rhodium catalysis was primarily done by Dr. Hormos Azizian. Then a number of people that worked very much on the ruthenium catalyst and on the additives. The osmium work was done primarily by the people near the bottom of the list. And most of these people have found very nice positions in industry or in academia. And they certainly were the real important thing in making this project work. finally, of course, without financial support, we wouldn't be able to do any of this. A lot of the fundamental work that we have done over the years, and a lot of the related work, certainly we have to give great thanks to NSERC for their continuing support. I list Bayer Incorporated here, but this goes back to many years ago when it started out as Polysar, went through Nova, and now through Bayer. So essentially I've been working with three companies, and many times I thought they were going to chop when there's a change from one company to another, but we've always made it through quite well, and there's always been very, very good support to continue this process. And finally, I acknowledge my own university, who has provided excellent laboratory facilities